220 volts alternating current output voltage of the inverter dictates the operating voltage for the entire panel it feeds. Consequently, all circuits within the panel will function at 220 volts alternating current. The panel cannot support a mixture of 120 volts and 240 volt circuits when supplied by a 220 volts alternating current source. Every circuit connected to the panel will operate at 220 volts alternating current. The 4C-2 cable facilitates the transmission of 220 volts alternating current power from the inverter to the panel. This cable comprises 4 conductors. Firstly, 2 hot conductors, typically colored black and red, each rated for 220 volts alternating current. Secondly, a neutral conductor, usually white, and thirdly, a ground conductor, which is either green or bare copper. The #2 American wire gauge, AUG, designation of the conductors signifies their capacity to handle substantial current loads necessary for the critical equipment linked to the panel. The panel rating, specified as 120/240 volts, 250 amps maximum, indicates 2 key aspects. Firstly, the panel is engineered to function with either 120 volts or 240 volt systems, and secondly, the highest permissible current flow through the panel is 250 amps. However, with the panel connected to a 220 volts alternating current power source, its actual operating voltage aligns with 220 volts alternating current. The maximum allowable current is governed by the limitations of both the 4C-2 cable and the circuit breakers installed within the panel. Therefore, in this configuration, the entire panel operates at 220 volts alternating current. Mixing 120 volts and 240 volt circuits is not viable. The 4C-2 cable is dedicated to conveying the 220 volts alternating current power from the inverter to the panel. The panel rating offers insight into its maximum voltage and current handling capabilities. Let's delve further into each of these aspects. The inverter's output voltage being 220 volts alternating current unequivocally sets the standard for all circuits within the downstream panel. This is because the panel is essentially a distribution point, and it simply passes on the voltage it receives. Think of it as a water pipe. If you pump water at a certain pressure into the pipe, that pressure is what will be available at the outlets along the pipe. Similarly, the voltage from the inverter is what energizes the circuits in the panel. Trying to create 120 volts or 240 volt circuits from a 220 volts alternating current source within the same panel would require additional transformers or voltage dividers, which are not typically part of a standard panel setup. This would introduce unnecessary complexity, costs, and potential points of failure. The 4C-2 cable plays a crucial role in safely and effectively delivering power from the inverter to the panel. Let's break down its components. The 2 hot conductors, typically black and red, carry the alternating current. The insulation on these wires is rated to withstand the voltage and temperature conditions present in the application. The neutral conductor, usually white, provides a return path for the alternating current, completing the circuit. In a properly functioning system, the neutral conductor should carry minimal current. The ground conductor, either green or bare copper, serves as a safety measure. It provides a low impedance path back to the source in the event of a fault, such as a short circuit. This allows the overcurrent protection devices, like circuit breakers, to quickly trip and energize the circuit, preventing electrical shock or fire hazards. The #2 American wire gauge designation refers to the cross-sectional area of the conductors. A larger gauge number indicates a smaller wire diameter, and vice versa. The #2 American wire gauge is capable of carrying a significant amount of current, which is necessary to supply the critical equipment connected to the panel. The specific ampacity, or current carrying capacity, of the #2 American wire gauge wire depends on several factors, including the insulation type, the ambient temperature, and the installation method. It is essential to consult the National Electrical Code, NEC Table 310.15b16, or the wire manufacturer's specifications to determine the appropriate ampacity for the specific application. Now, let's discuss the panel rating of 120/240 volts, 250 amps maximum. This rating indicates the panel's design parameters, but it does not override the actual operating voltage determined by the inverter's output. The 120/240 volts designation means that the panel is constructed with components and insulation suitable for use in either 120 volts or 240 volt systems. However, since the panel is being fed with 220 volts alternating current, it is effectively operating as a 220 volts panel. The 250 amps maximum rating specifies the maximum amount of current that the panel's busbars, which are the conductive bars that distribute power to the circuit breakers, can safely handle. Exceeding this current rating can lead to overheating, insulation damage, and potentially a fire hazard. The actual current that the panel will carry is determined by the loads connected to the circuit breakers. It is essential to ensure that the total load does not exceed the panel's rating or the ampacity of the 4C/2 cable, whichever is lower. The circuit breakers in the panel provide overcurrent protection for the individual circuits. They are designed to trip or open the circuit when the current exceeds a predetermined level. This protects the wiring and equipment from damage due to overloads or short circuits. The 15 amps, 20 amps, and 30 amp circuit breakers indicate the maximum current that each circuit can safely carry. It is crucial to select the appropriate size circuit breaker for each circuit based on the load and the wire size. Using an undersized circuit breaker can lead to nuisance tripping, while using an oversized circuit breaker can allow excessive current to flow, potentially damaging the wiring and equipment. In summary, the inverter's 220 volts alternating current output establishes the operating voltage for the entire panel. The panel cannot accommodate a mix of 120 volts and 240 volts circuits. The 4C/2 cable is responsible for delivering power from the inverter to the panel, and its ampacity must be sufficient to handle the anticipated load. The panel rating indicates its design parameters, but the actual operating voltage is determined by the inverter's output. The circuit breakers provide overcurrent protection for the individual circuits. To ensure safe and reliable installation, it is essential to adhere to the National Electrical Code (NEC) and all applicable local codes and regulations. Always consult with a qualified electrician for any electrical work. Let's consider some additional factors that may be relevant to this setup. The type of inverter being used can affect the power quality and the suitability for different types of loads. Some inverters produce a pure sine wave output, which is ideal for sensitive electronic equipment. Other inverters produce a modified sine wave output, which may be less expensive but can cause problems with some types of loads, such as motors and fluorescent lights. The grounding system is another important consideration. The grounding system provides a path for fault current to flow back to the source, allowing the overcurrent protection devices to trip. A properly installed grounding system is essential for safety. The location of the panel and the inverter can also affect the installation requirements. For example, if the panel is located in a damp or wet location, it must be rated for that environment. Similarly, if the inverter is located outdoors, it must be protected from the elements. Regular maintenance is crucial to ensure the continued safe and reliable operation of the system. This includes inspecting the wiring, connections, and circuit breakers for any signs of damage or deterioration. It also includes testing the inverter and the batteries, if applicable, to ensure that they are functioning properly. It is also important to keep the panel and the inverter clean and free of dust and debris. This can help to prevent overheating and other problems. When working with electrical equipment, always follow safe work practices. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves. It also includes energizing the circuit before working on it and using a voltage tester to verify that the circuit is de-energized. Never work on electrical equipment if you are not qualified to do so. Electricity can be dangerous, and it is important to take precautions to protect yourself and others. Let's talk about a few common issues that might arise with this type of setup and how to troubleshoot them. One common issue is nuisance tripping of the circuit breakers. This can be caused by several factors, including overloaded circuits, loose connections, and faulty circuit breakers. To troubleshoot nuisance tripping, firstly, check the load on the circuit to ensure that it is not exceeding the circuit breaker's rating. Secondly, inspect the connections to ensure that they are tight and secure. Thirdly, test the circuit breaker to see if it is faulty. Another common issue is voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source. This can be caused by several factors, including long wire runs, undersized wiring, and high current loads. To troubleshoot voltage drop, firstly, measure the voltage at the load and at the source. Secondly, check the wire size to ensure that it is adequate for the load and the distance. Thirdly, reduce the load or shorten the wire run if possible. A third common issue is overheating. Overheating can be caused by several factors, including overloaded circuits, loose connections, and inadequate ventilation. To troubleshoot overheating, firstly, check the load on the circuit to ensure that it is not exceeding the circuit breaker's rating. Secondly, inspect the connections to ensure that they are tight and secure. Thirdly, improve the ventilation around the panel and the inverter. In addition to these common issues, there are other potential problems that can arise with an inverter-based power system. It is essential to have a qualified electrician inspect the system regularly and to address any problems promptly. Remember, electrical work should always be performed by qualified personnel who understand the risks and have the necessary training and equipment to do the job safely. Never attempt to perform electrical work if you are not qualified. Always consult with a licensed electrician for any electrical installations, repairs, or modifications. This narration provides a general overview of the topic and should not be considered a substitute for professional electrical advice. Local codes and regulations may vary, so it is essential to comply with all applicable requirements.